So the second half of today's lesson is looking at this idea of integrating composite functions, but ones that aren't perfect. So we did 4 examples in the previous video where they worked out exactly the way you hope they work out. And as you would probably guess, they're not all going to be that perfect on an AP test or on an assignment. So let's talk about what if they're not and how do we fix it. So these examples are going to be, I call them U sub with adjustments, or it gets like imperfect U sub. We still start them the exact same way. So our goal is still to say, what is that inner function? We're going to call that the U piece. So it should be pretty easy to identify with these. Polynomial-based ones are very easy to see what's that inner function. And then you're going to write down what is your derivative of that function. And here's where things aren't so perfect. When you look at your original integral, it doesn't have the 2 there. It just has a dx at the end. So what we have to do when we sub in dx, we need to not have that 2 in front of it. So the way I adjust it is I divide both sides by 2. You'll hear me refer to that a lot as a 1/2 adjustment or a constant adjustment of a half. So now what I do when I start replacing everything, my u piece is being taken to the 1/2 power because it's being square rooted. And I'm going to replace the dx with what I know dx to be, which is this 1/2 du. If you have a coefficient, it is always allowed to go in front of the integral sign. So we're going to actually put that adjustment in the very beginning. And then I'm still going to put my du here, again, showing that it is in terms of u, and I did double check on that derivative. From there, I'm going to just do a power rule. So power 1 greater divided by that power. So that's going to be power 1 greater is going to be u to the 3/2 divided by 3/2. I'm going to clean it up a little bit. So I'm going to have 1/2 times 2/3. My 2's will cancel. So I get 1/3. And then I'm going to put my u back in. So my u was 2x minus 1 to the 3/2 now plus c. When you're done with a problem like this, again, to check your work, you can do a chain rule. Power out front, power 1 last derivative of what's inside. If you ignore this adjustment, you will not get what you originally started with. You'll be off by a coefficient. You will have the wrong constant in front. So doing something small like that and checking for that adjustment is going to be what ensures that you can actually check your work and you get what you started with. So, and it takes a little while. The first one is always, so you might be sitting there going, I have no idea what you just did. I promise they get a little more comfortable the more you see. So the next one, my u is 2x cubed minus 4 because that's my inner function. The derivative is 6x squared, sorry, not cubed. I don't have a 6x squared dx, I have an x squared dx. So I've got the x part, which is great, but I don't have the 6. So to get rid of that 6, so I can see what does x squared dx actually equal, I would just divide both sides by 6. So we would say that it is a 1/6 adjustment. Then I'm going to write down what's being done to u. Well, it's being taken to the -4th power. Power 1 greater divided by that power. I want to clean this up. I also want to put the u back in so I'm not taking up too much space. So when I clean it up, I end up with a -1/18th, and I end up with the u in the bottom being cubed. So I end up with -118, and I'm just going to put parentheses 2x cubed minus 4 cubed plus c. This negative exponent moves it to the bottom. Again, if I want to check my work, I would do a chain rule with my final answer and I would get what I started with. If I neglect this constant adjustment, I would not get what I started with. I would be off by a constant. That little step is just guaranteeing that you actually have the right piece to begin with and the right final answer. Same thing here. So this one, my u is 4x cubed plus 7 because that is what is the inner piece. The derivative of that is power out front, power 1 less, is 12x squared. But I'm not replacing a 12x squared. I'm replacing a 3x squared. So to replace a 3x squared, I'm going to divide both sides by 4. What that does is it gives me what the original problem has in its integral. It gives me a 3x squared dx. So now when I replace everything in u notation, I'm going to have a 1/4 adjustment. My function is being taken to the third power, and I have ensured that everything is in terms of u, and I've checked for that adjustment. So power 1 greater divided by that power, a lot of power rules today, gives me 4x cubed plus 7 to the fourth over 16. You are also welcome to write it as 1/16 and then the 4x cubed plus 7 to the fourth. And again, chain rule would process that and show you that you get what you started with. I'm going to show you a couple ways to do this next one. So my u is 2x plus 1. That's the inner function. The derivative of that is 2. So here's what kind of drives me crazy. I have a 2 is what I'm supposed to be replacing, but I start with a 7. Those numbers are not very compatible. So here's what you can do. Since that 7 is just a constant, it is perfectly legal to bring the 7 all the way to the front of the integral to start. Anytime I have a number there, especially numbers that are just kind of messy, I just get it out of my way. Now, when I make my adjustment, I just have a dx left, so I'm going to divide by 2, do a 1/2 adjustment, and have that as my constant that's out front. So I kind of do it like in parts. I bring that 7 that's kind of bothering me out front, and then I do the adjustment. The other option is if you want to, basically, if you want to go from a 2 to a 7, you could multiply both sides by 7/2, and that would give you that coefficient adjustment. My u is being taken to the -2. So I get, oh, I don't want to write my integral sign again. I get u to the -1 over -1. I still have this constant out front, so I'm just going to leave that constant out front. So u to the -1 over -1, which gives me -7 over 2. And then I need to move the u to the bottom, so 2x plus 1, and it's just to the first power, plus c. You still have a composite function at the end if you had a composite function in the beginning. A few more. I want to try to show you a decent amount of these because I feel like it takes 3 or 4 before your brain starts processing what's actually happening because it just feels kind of different. So this next one, my u is 3 minus x. The derivative is -1 or just negative dx. I don't have a negative. I have a positive dx. So this adjustment, I often call this a negative adjustment. You basically get rid of the negative by either dividing by a -1 or multiplying by a -1. And so my adjustment that goes in front of this integral, because it's basically the wrong sign, is a negative adjustment. That's actually a very common simple adjustment, is just a sign adjustment. It's being taken to the -5th, so I get u to the no, not -6, -4. I'm just as guilty as my students sometimes when it comes to thinking backwards. So power 1 greater divided by that power. These negatives are going to cancel. You're also going to move the u to the bottom, so your final answer is 1 over the quantity 3 minus x to the fourth plus c. I want to show you this number 10. I'm trying to, in these last few examples, show you just different variations of things that happen. This one just is kind of bigger. It's not harder. It's just kind of a bigger setup. So my u is just a larger expression. It's 4 plus 2x plus x squared because it's all under a square root. The derivative of that is 2 plus 2x. If you look at the original problem, you don't have a 2 plus 2x, you have a 1 plus x. Well, we can adjust that by dividing everything by 2. If we do a 1/2 adjustment, we will get 1 plus x, which is exactly what's in the original integral expression. So I have a 1/2 adjustment. It is being taken to the -1/2 power because it's in the bottom being square rooted. So power 1 greater divided by that power. So power 1 greater would be the half. Dividing by a half is the same as multiplying by 2. Be careful when you're working with fractions and negatives. So power 1 greater divided by that power. The 1/2 and the 2 will cancel. So my final answer is this big expression, this u, which is 4 plus 2x plus x squared. And the whole thing is to the half, or you could put the whole thing under a square root. If you were to do a chain rule with this, you would get right back to where you started. You would do power out front, power 1 less, derivative of what's inside, and it would simplify to that original problem. So here's our last two. Again, trying to show you just different variations that happen so you start to feel more comfortable. I still think the choice of u should be pretty simple for you. So u is 6 minus 3x squared. The derivative of that is negative 6x. I don't have a negative 6x, I just have a plain old x. So I need to divide by negative 6. So I have a negative 1/6 adjustment, and that's what I'm going to replace x dx with. So you can almost break it up into parts. Like, this is what I'm replacing my constant adjustment with. This is my u piece that's being taken to a power. So when I write it out, I'm going to have negative 1/6 u to the 1/2 du because it's being square rooted. Power 1 greater will be 3/2 divided by 3/2 is going to be 2/3 u to the 3/2. Clean it up a little bit. You don't have to reduce, although I think on Delta Math it actually wants you to reduce. The College Board doesn't care. This reduces to negative 1/9, and then put your u piece back in. So 6 minus 3x squared to the 3/2 plus c. Our last one looks like it's going to be pretty bad. It actually ends up working out much simpler than you would expect. So your u is 1 over x plus 4, because that's the inner piece being squared. So the derivative of that, derivative of 1 over x, you might want to come off to the side and think of it as, well, it's actually just x to the negative 1 power. So power out front, power 1 less, gives me a derivative of negative 1 over x squared. Well, you actually almost have that. You have the x squared on the bottom, you have the dx, you don't have the negative. So this would be another example of a negative adjustment. The only thing that you are missing in the original integral is a negative sign. So we're going to make that negative adjustment. It is just a u squared du. So it ends up a little easier because you don't have a fraction exponent or a negative exponent. So you get negative u to the 3rd over 3 when I do my power rule. So my final answer, and you can put the negative anywhere you want, is negative the quantity 1 over x plus 4 cubed over 3 plus c. So this is that process of u substitution. It is something that we're going to continue to reference throughout the rest of the course. I do want to mention before I shut off here, I will have students that after they learn this will try to use u substitution for every integral out there. And I want to make sure that just because you learn something new, you don't feel like you need to use it constantly. This is only going to be necessary when you are working with a composite function that's being integrated. So I've seen students that will be given problem from like earlier in the chapter. That was really messy writing, where it was something like this. And students will say, well, gee, what do you think the u should be? Well, there is no composite function. You do have to do some algebra. You have to distribute, but there is not a function inside of another function. You just have functions you can multiply. Same thing if you had something like this. If you had like an x cubed plus x minus 2, and the whole thing was over x. That's not a composite function. You can simplify it, you can pretzel it and break it down, but all of your functions will just be individual terms. None of them will be composite functions. They'll be singular functions. So make sure that you are only doing this when you have a composite function that's being asked to be integrated. It's not necessary when you have a function that maybe is just an algebraic example or some single function, not composite function problem.